Hello, all my JavaScript friends. This is the Virtuoid, aka Mike Smith, and this is our table object. So last time we took a look at the game object. This time we're taking a look at the table object. So I'm just going to give you a fair warning. You better sit down and strap in because we may be in for a long ride here. Let's take a look and see what we have. So remember that the whole purpose of the table is to be able to hold the jigsaw puzzle. That means it's going to hold the image. It's going to hold all the pieces. It's going to hold the cut. It's going to determine once a piece has been moved, whether it has been connected, whether it's connected to one piece, whether it's connected to multiple pieces, whether it's part of a multiple piece that's connected to a single piece, whether it's part of a multiple piece that's connected to multiple pieces, whether it's a multiple piece or a single piece connected to both a multiple piece and a single piece at the same time, and so on and so on and so forth and whatever. Now, if you saw our unit test there, you saw that our unit test actually ran and worked. Yay! So it looks like we got everything here at least covered the best that I know of. But let's take a look at the class itself. It's very simple. The idea here, remember, the game is creating the table and it's going to pass to it the image and the cut and none pieces. So that's going to be the very important thing. And here that is right here. It's got to be able to pass the image, the cut, and none pieces. And what we need to take a look at here with the table, once it gets something in from the game, it's going to have to basically say, I've got an image here. I need to cut it based upon this particular cut, and I need to shuffle the pieces, and then I need to know when a piece is moved so I can do whatever I have to do. So let's take a look at it. Again, I've got getters here. Again, like with the game, no setters. What I'm trying to do here is I'm trying to make everything as read-only as possible. And the reason I'm doing that is I want to try to limit the access that outside objects will have to this particular object. So there are no setters, there's only getters. Okay, we add a piece. All right, the pieces are done in this happens to be a two-dimensional piece or two-dimensional puzzle. So we are adding a piece based upon a row and a column coordinate system. So what we do expect is that the piece to have a certain ordinal place to it. And we determine whether pieces, we make sure that our pieces array is set up as a two-dimensional array. And the two-dimensional array basically says, hey, here's my ordinal piece. This is my row. This is my column. I'm saving out the piece. And then I set the piece within pieces ID. Well, I'm sorry, set the piece within pieces. So that's going to be a simple array. But I'm also keeping an array of pieces ID, and that allows me to be able to very quickly find a particular piece based upon the ID. Because what will happen is that I'm storing this ID on the DOM of the piece itself so that when it is clicked and dragged, and the UI sends to the game saying, hey, I've moved this particular piece. Here's the ID of it. The game is going to come to the table and say, I need this ID piece. And by getting the piece based upon the ID, I can find it very, very quickly. That way I couldn't care less where it was on the screen. Here's the cut puzzle. It's very, very, very simple. The cut puzzle needs to be called before anything else is called. And that allows us to be able to cut the puzzle itself. And this will just basically do, here's rows, here's columns, here's the position. The default position is going to be basically laid out in a two-dimensional array. The ordinals are going to be set, and they never change, but they're going to be set to the H and I and the I and the J. And the X and the Y are going to be set to our piece width and piece height times the I or the J, which is the rows and the columns. I should have said row and column here to make it a lot easier. I didn't, and I'm not going to change it right now, but hey, if you want to do that, go right ahead. Very important to get piece by ordinal. Why is that important? Because once I get a particular piece and I'm trying to set a connection, I have the ordinal of the piece I want to connect it. It's very easy to be able to grab a piece based upon the ordinal. So all I have to do is just say, hey, give me a piece that's at ordinal position 0, 0, or the piece that's at ordinal position 6, 2. And this will allow me to grab the pieces. And all that is saved within the pieces array. Here's the get piece by ID, which comes from the ID. We already talked about that. Here's where the actual fun begins. That was just all preliminary stuff. Actually, it's not quite preliminary stuff. Let's just skip ahead for a second here. Set puzzle dimensions. I want to get to move here just a minute. When set puzzle dimensions, it allows me to set the dimensions of the puzzle itself. This is the size of the puzzle. And so here's the shuffle puzzle. It's very, very simple. I just sit there and flatten out the array and then move each individual piece based upon a random number. How do I determine whether this piece is out of bounds or not? Well, that's within the move section. Because remember, if you remember the video that we had for the spreadsheet, excuse me, the video that we had of the PowerPoint display, I always said that one of the things the table returns to the game is that whether a piece has been moved or not. And that piece has been moved basically means that this piece was placed down by the UI out of order or out of range, and I'm moving it for you back within range or within the boundaries of the puzzle. Move will do that for us automatically, so we're not checking here whether we've got something out of bounds or not. Dispatch event. This is the dispatch event that allows us to be able to figure out that something has occurred, and within it we just got one event, the in-game event called piece moved. This is the in-game event that comes from the game. It basically says, hey, we've moved a piece here, so we got to move this particular piece to this particular section, and blah blah blah, and all that kind of fun stuff. Alrighty, let's get to the move. That's the biggie. Okay, this is actually called when a piece has finished its move. It can also be called when it's time to physically move a piece. All right, lots going on here. The real key here is that we're passing the piece we want to move and the new position, and this is the physical position of this piece. We first determine the X and Y coordinate based upon whether we had the pieces out of bounds or not. So X and Y is going to come back and say it could possibly be out of bounds, in which case it is moved. And this is where we get the status of no change in moved. So if the puzzle is out of bounds, X and Y is going to change. And so I check to make sure X and Y is the same or different from the original position. If it is different, we're going to return a status moved by default. Otherwise, we're going to change a status no change. And the status move is going to be transmitted back over to the UI saying, hey, this piece actually was out of bounds. You need to shift it over and move it just a little bit to get it within bounds. No problem. Okay, so the first thing we're going to do is move all pieces, which quite honestly, I think I really don't need anymore, but I'll have to take a look at that. I just suddenly realized I may have an error within the program. Well, not an error. Everything still works. It's just that I may be duplicating something I shouldn't be duplicating. But that's part of what triage is all for once you get, or debriefing once you get everything done. Then we're going to check all the connections. That's one of the things here, because now we move the pieces. We got to check to make sure we've got some connections. So we do the check all connections, and with the check all connections, it basically runs a check all connections of the parent first. If I have a parent, it's going to check all the connections of the parent. I'm not going to check anything else. Then I'm going to check all of my children. And in reality, this is actually code that's kind of duplicated here too that I really shouldn't need to have, but that's just the way it is. But the idea here is that basically all connections is returned. And once we get all connections is returned, okay. We're going to check all connections. We're going to check all connections of the piece parent. And once the piece parent's done, we're going to go for each one of those connections and push that connection into all connections. Then we're going to go through we're going to go through the children of the piece and also check the connection of each one of those children. Once we get all that, we're going to return all connections. And this will return every single possible connection within the system or within the children, whether you're a parent or a child. Check connection is what gets you within this routine here. You notice that there is a check connection routine. That's the big thing. This is a little bit recursive, and that's the whole idea. It is recursive. But we do the check connection. That's where we do the physical connection on each individual piece. Now, if you remember from the PowerPoint presentations, I said we check 4 ordinal positions: north, south, east, and west, or north, east, south, west in that order. This is where I do it: north, south, north, east, and west. I got a routine here called check piece connection, which checks the piece. It checks the ordinal that we want to do. For instance, in north, y is subtracted 1. For west, which is what this is, x is subtracted 1. And then I have what we call a multiplier. And this multiplier is going to basically say, all right, I know that if these two pieces are close to each other, that since I'm checking the northern side, the X values should be pretty much right on top of each other. I mean, they should be exactly the same. But the Y values are going to be an entire piece height away. So therefore, I'm going to, when I get to it, I'm going to multiply the height by -1, saying, the Y of the piece being checked is going to, I expect it to be a piece width lower than the one I'm checking. And the same thing with the east side, in which I expect the X to be a piece width higher, piece height higher, and a piece width lower for the west. Once I get all of those, I check to make sure I do an initial connection, or I do a status no connection if there's been no connection. Otherwise, I do a status initial connection and return a status initial connection, which allows me to say, hey, I've got a north, south, east, and west connection for this piece. I've got a new connection of the piece. So north is either going to come back to say status connected, or status, or either one of those are going to come back with status connected. Once I get to the check piece connection, which I'm passing the from piece, the ordinal that I'm checking, and then the check X, check Y multipliers, and make sure that everything is valid. If it's not valid, I'm just going to do a connection. Get the piece by ordinal. Then I'm going to run through each one of the children itself, and then I'm going to run through each one of the children, and then I'm going to return a status of no connection if the from piece has a child, or the to piece has a child from piece. Basically, I want to check to make sure that each one is not a child of the other. Because, for instance, if you have two children that are with a parent, and you're checking connection of one of the children, the idea here is you don't want to check connections of your siblings or even of your parents. So that's what all this checking does right here, is to make sure I'm not a child or a sibling or a parent of any of the other pieces. Otherwise, I'm not going to check. So at this point, it's a valid piece. I then get what we call the checking point. And this checking point is something that is internal within each piece that basically says, this is the physical connection I'm going to check. And that will allow me to draw these really funky lines all over the place without having to worry about whether the lines are not. From my personal point of view, everything is still a simple two-dimensional square piece array, and I'm just checking those pieces. And so I have placed within each piece a checking point, in which each checking point is an exact width and exact height away from each other. That way, I can very quickly and easily check to find out if two pieces are connected to each other. So I just do a quick little distance, and if the distance is within a tolerance mode, and what's this tolerance mode? Let's skip all the way to the top, and our tolerance is default to 3 pixels. So if it's within 3 pixels, I'm going to consider it a connection. If it is a connection, it's going to have to be moved, because one of the ideas here is that if you connect into the other piece, you're already at least three pieces apart. It's going to have to move to connect. So that's what's going to happen when we get the status back to connection. So we're going to return the status. So if the distance is within the tolerance, we're going to return the status connected. And then once that status connected is done, it's going to go back up to the check connections. It's going to then go back up to the check all connections. And then once that all gets done, it's going to go finally back up to the move. Whew, there we go. And it's going to look through all the different connections. And if it is a status no connection, then I don't worry about it. But if we do have a status initial connection, then we check the north, south, east, and west. If the status is connected, then we make sure that the pieces. Then if the status is connected, this whole section right here will remove the from piece to make sure it matches up to piece. Because remember, we have a tolerance of 3 pixels. So what if our piece comes within 2 pixels? Well, we just can't have it as 2 pixels. So we got to move the from piece to adjust itself automatically to make it line up correctly with the piece that we're connecting to. And then, of course, we're subtracting a piece. And then finally, if no connections equal connection length, then we do a status of, then if we get a status of moved, we're going to return a status moved. Otherwise, we're going to return a status no change. If the pieces remain to 1, we're going to return a status finished. Otherwise, we're going to return a status connected. So basically, here are the 4 things we're going to return from a move. We're either going to return saying this particular piece has been moved because it got dropped off the table. This particular piece had absolutely no change whatsoever, so it basically is a piece that you moved and everything's fine. It can be connected, which means this piece connected with another piece. And here's all the information you need to know about the connected piece. And finally, we have status game finished because, hey, the game is finished because there's only one piece left. And in each one of these statuses, I basically give you information that is either a from piece and pieces remaining, and in some instances a new position, because for instance what we need to know, if we have a status move, we need to have a new position there too. So most of these statuses will always have pieces remaining and a from piece, but they may have extra information too. So that's what the move does. So when the UI sits there and drags a piece, it's going to go to game. Game's going to go to table. Table's going to say, okay, I'm moving this piece. Oh, does it have any children or a parent? We got to move them too. Oh, once we drop that, does it connect with anything? Oh, if it does, then great. But has any other pieces connected also? So we got to check all the other pieces too. So this whole routine here, the entire convoluted section of it, is to be able to sit there and say, I have moved this piece and I have made a connection to some pieces somewhere until the final remaining piece is one, in which case we do a game finished. And that's basically all there is to the table. So the table doesn't really do a whole lot. The table just takes the pieces, it moves the pieces around and tells the game whether there's been a connection or not. That's it. Now, the convoluted part is trying to figure out the connections. I mean, you can tell 3/4 of this code is just to try to figure out to make sure the connections are done correctly. And it is convoluted. And even going through it here, talking about it, I already noticed 2 little errors that I can fix a little bit later on if we ever do a secondary deep dive into this thing, which right now I'm not planning on it. You know, I'll leave that one up to you. But that's basically all there really is to the table object. Next time, we're going to take a look at the piece object. Thanks for watching. Subscribe to this channel to view more videos. Click on the like button on this video and visit us at TheVirtuoid.com. Also, support us on Patreon, where you can get access to member-only videos. Links are down below. Again, thank you very much for watching, and keep on coding.